So hello, today we will focus on the introducing the X compiler source. You can check out the whole compiler source on github.com X Foundation X. X compiler is written in OCaml. You can get all the instructions for building from source on using the README on the GitHub page here. You get different building instructions for Lexing, Linux, and Windows. Today we will not build the source of the X compiler. It requires installing different software, which I have not yet on this computer. X compiler is written using OCaml programming language. OCaml is a high-level functional programming language, which is great for symbolic processing, which is what the X compiler does. Actually, the whole source of the X compiler, which you can find here. Here is a fresh checkout I made from the GitHub sources of the X compiler. And if you look at the source directory, you will see it's just under 3 megabytes of source for the whole compiler. So the whole, all the platform supports, all the different platforms, and all the macro interpreters. So it's very small compared to, for instance, if you have written this in C++. I guess it would take around 10 times the amount of programming of programs to have this in C++. And also it enables us to have really safe compiler, because you cannot crash an OCaml application. It's very safe. You don't get memory access, but you get still very fast optimization. So the X compiler is very fast, as you may know already. We look into the sources. So here I have a hxproj, which is an xdevelop project file, which I will open. You will see that it's right now it's focused. It's configured to build on Windows, but you should be able to modify here in the build properties. Right now, you use MSVC and Makefile Win, but you should be able to use different Makefile and compilation parameters to build on Linux, for instance, or on other platforms. If you're using this OS. You have several directories, top-level directories. The test directory contains all the unit tests for the X compiler, so you get all these unit tests here. A lot of issues for regression. So every time we use continuous integration, so every time we change something in the compiler, we get reports in case we break something, which is very nice. Thanks to Andy for that. Also, we have you have standard library of Haxe, which contains only hx file. So you have all the array, string, extra, and the platform-specific package. So you get all the standard library class that ships with the X compiler binaries here, and you get libs, which are additional library we are using in the X compiler. So, for instance, a Swift lib for handling the Swift format, a tree type thing, XML, zip, and a few other libraries we are using in the compiler. And here are the source of the compiler, which is the source directory, of course. And you get ML files, which stands for OCaml. So here you get an example. OCaml is maybe a bit hard to read at first when you're not used to it. But when you somehow master it, it becomes quite easy to write, and you can express a lot of things with a very few lines, which keep the code quite compact. So you have the pattern matching with a match. You have let is to declare variables and function. You don't have brace around function, which is maybe a bit hard because you have to figure out when the function stops. It's a bit less easy to write. So here is a source of compiler. So you have several directories. You have main.ml, is responsible for parsing the command line. So here we can see, if you scroll down a bit, here you can see all the like command line. This is a bit more here. You can see all the command line cp, gs, with C++, xml, main, lib, -d. So here are the command line, all the command line parsing and dispatching. So you have a lot of options here for the whole command line of Haxe. And here we basically we start the compilation and we dispatch and we capture the error and print it. So this is what main does. It also handles the compilation server somewhere here. So it doesn't do much. Usually you don't have to change much things here. Then we have several directories. Typing take care of typing the code. The syntax is about parsing. Then you have optimizations, classes or modules actually. Then you have every macro interpreter, and then you have the generators, which are for each platforms when we have finished compiling, or do we generate the code. So just to give you an overview of the steps involved in compiling X program, the first step is what we call Lexing, which involves translating the string, which is your X file, into a series of tokens. So you go from a X file, for instance, if you have a class foo. So your program is a string at first. It doesn't have any sense for the compiler. So here you translate this into tokens, which are a class. This is the first token. Then you have another token foo, and so this is a keyword. So it will be a keyword class. Then you get an identifier foo, and then you get brace open and brace close, for instance. So basically, Lexing does that to your program. It transforms this string into a series of tokens. And this is done into the syntax lexer file, which match this kind of regular expression. So you have all these regular expressions, and it translates that into tokens, which you can see here. The second step is about its parsing. Parsing will translate these tokens into what we call an IST. An IST, so you get from tokens into IST. An IST is a shortcut for abstract syntax tree. So it will translate this into something which say a class foo and etc. So here are the fields of the class. So if you have a field, for instance, it will be var x and function foo, and here you have more things. So this is an IST. So it's more like a tree. It gives you a lot of informations of it's a memory, like an enumerable representation of your program. So if you are used with macro, you are used with IST, because macros actually manipulates this IST. So it takes this IST as input and return another IST. So parsing is done here. So you have here the IST, which is declared in ist.ml. You get this is all the metadata. These are the keywords for Haxe. These are all the binary operations. So addition, multiply, divide, sub, assignation, equal, greater than, etc. So, and you have all the tokens here, which come from Lexing, and here you have the IST. So IST for expression, you can make a constant, an array, a call. So a lot of different things. It's quite a lot of definitions. And here at the top level, you get definitions which are class, enum, type, def, abstract, import, and using, which are the top level definition you get in a module. So the parser will translate these tokens into the IST, and then you will do typing. Typing is done into the typing classes here, or the typing modules here. It will translate the IST into a typed IST. The typed IST is the same, pretty much the same IST, except that we have somehow validated it with types. So every part of it have a lot of types, which is somehow an untyped IST because you don't know yet if it's correct or not. But typing will just do all the checking that your variables names are actually declared, that that you get the function you call actually have the good arguments and everything. So you can see here in type.ml you get a definition of a type. This is a type in Haxe, type T, and you have all these typed expression here, which are the typed IST, and you have also like what is a class. So a class have a lot of things. It have a path, it have a module, it have metadata. It can be it have a superclass, implements, it have fields, it have statics, you have a lot of different things, overrides. So you have all this classing, you have enums also, you have abstract, and you have a module type which can be a class, an enum, a type, def, or abstract. And then a definition of a module which contains several of these types. So this is basically what the compiler is doing. It translates the previous IST into something which is more structured, which is typed IST. And then you have a generation, then you have optimization, which will run on the typed IST. So it will get a typed IST as input and return another typed IST, but this time optimized. So in optimization, we have the analyzer, which is an optimizer which takes care of optimizing all the common definition via propagation, or a lot of optimizations done directly on the IST. This is written by Simon. You have another optimizer here, which we will inline a few specific API with more like optimized code. For instance, if you use a type enum index on a constant enum, it will automatically replace it with the actual integer of the enum. So you don't, if you know, it doesn't have to do anything at runtime. If you use, for instance, std int of an int, then you don't need to do anything. If you do std string of a constant, we can directly convert it to a string without having to do, again, runtime string conversion. So you get a lot of these kind of optimizations for Haxe compiler. So this is more like by hand optimizations, but there is a few of them that does this. You have also like inlining here, which is under here, which does the inlining of function call. Maybe I will do a talk on this at some point. And so here you get your final IST, which is optimized, and then you will start doing the final thing, which is a generation. Generation will take one of the generators here. So you have a S3, CPP, C#, Ashel, Java, JS, Neko, PHP, Python, Swift and Swift 8, and XML. So it will take the typed IST as input, and it will compile it to platform code. So if it's it can be a big output JavaScript. It can be a lot of C++ classes, etc. So it can be a lot of different things depending on the platform. So as you can see, adding a new platform to Haxe is just somehow adding this part. All these parts are already done and are already done in common for all the platforms. So when you add a new platforms, you need a generator, and you need also a lot of standard library support. But all the compiler is works exactly the same with a few minor change, depending, for instance, if you have a null int or not. So you get a few configuration, but apart from that, you get all these things which are done exactly the same, whatever the platform you're compiling to. And I think that's most of it. We can look a bit at the source now. So we'll start with maybe from the start, the Lexer. So I say the Lexer. The Lexer here, as I showed you before, I'll zoom in a bit, have here a lot of regular expression, and we translate that to binary operation. And it will pass also the strings, and well, it have a lot and regular expression also. If you have a regular expression here under all the escape sequence and these kind of things. Then it goes into the parser, which use an extension of the OCaml syntax, which called CamelPick4, which is this syntax. It's unable to have what's called stream parser. So it's for people familiar with language grammar, it's a LLK parser. So you can capture the token and return and build the IST like this. So for instance, parse file, we start in parse file, and we look if we had a keyword package, we will parse the package. So parse package will do its own thing, and then we look at the package, and if we have an indent here, it means that we must start with a lowercase character if we have a remaining indent. If not, we have a semicolon, and then we have type declarations. And if we don't have a keyword package, it means we can have directly the type declaration here. So here we get into a list of declarations. So we pass one, and then we pass the other one, and we have a try catch. We say if we have an exceptions, we can actually resolve the type pass which is raised using the import, which also help us to resume parsing errors to get proper completion, which is something which is a bit strange. Here you have different parsers, so you can have import, or you can have using, or you can have something which is an enum, and then you have brace open, brace close. So you see, here we are parsing the tokens and building the IST. So you have it's quite a big file. Every file in the Haxe compiler is pretty big because we didn't want to have a lot of files. It's a bit hard to handle a lot of files with OCaml because you cannot have two files referencing each other. So you need to have a strict ordering on your files, which makes sometimes hard to split the code into two parts, for instance. So the parser consists in one single big file that does all the parsing, and it's actually nice when you look at parsing errors to be able to quickly look at the jump between the functions and follow the logic without having to jump between the files. So yeah, that's about it for the parser. So this is way 1,600 file, 600 line files, and then you go into the typing. So typing is a bit is the more the biggest part of the X compiler, and maybe the most complex, because it involves like looking at all the types and resolving all the like compilation of the types. So here you see that the type definition itself takes so just the definition, so not implementation, takes 300 lines, and then you have a lot of utilities, functions, and one very important function here. You have printing, but the most important here is this one. It's called unify. Here, unify. This is a small function. It's not very that big. Here, take a few hundred lines, but it takes care of checking if you can assign a type, something which has a type A to a type B. So for instance, let's say I have my type A is an integer and my type B is a float. I can put an integer in a float, but I can't do it the other way. So here we will take care of all this for all the types. And it's actually quite complex things, because, for instance, if you have two classes here, you need to look at if one is extending the other, or if we have, for instance, if it's an interface, you have to look this, and you also have to check the type parameters, because you can have, for instance, an array of string here, an array of int there, so you cannot copy them, assign them. And you have function, and you have assigning a class to an anonymous or structure. So, and to anonymous, so you get like here structural to typing, and enums with abstracts, and well, a lot of things going on here. So that's quite complex thing. And unify is used a lot in the X compiler source. If you look into the typer, for instance, which is responsible for typing the expression, you can see, where can we see that? Here. So you see, for instance, we unify. Here is a unified call arguments. So you have a list of expression, and we have a list of arguments types with maybe optional flags, and we have to check that these expressions can go into this arguments type. Here we have unify min, which means we have a list of expression, and we want to know the minimal type of this expression. So for instance, if you have a branch that return a float in a if, and in the if you return a float, and in the else you return an int, we have to get somehow the minimal type, which is float for both, because that's the way things are. And here you have a lot of unification against going on. And finally, you have this big, this is still small thing, but you get this type ident is interesting. So I have an identifier which I know from his name, and if it's true, I get avec this tells this it's a const true if I'm accessing this as read. But if I'm trying to write to true, I have to return this accessor which say you cannot write to true, you cannot assign true. Same for false. For this, I have to check if I'm an abstract, or I cannot assign this. If I'm if I'm into a class, I can do that. Super null. And if it's not one of these reserved identifier, I will look into my locals, and if I found them, and if it's not found, I will look into my statics, and if it's not then I will look into the using for this, and okay, this is not member variables, then lookup in using, and then static variables, and then eventually I look into import enums, and finally I will look into the import globals, and finally if it's not there, it means it's not found. So you can see that even something which can be as simple, which should be as simple as I have an identifier and I want to know what it represents, actually involve a lot of steps, and it's the way we do that. We do things in the compiler. So one of the big thing in the typer, the most maybe central thing, is a bit down here. Let me check. I will look for it. Type exp. Here, this is a type exp, which means type the expression and convert this expression into the corresponding typed ist. If you remember the thing that I wrote before, I will just write it again. The typing takes an ist and output a typed ist. So here we get an ist, so we don't know yet what it does. For instance, if we have a constant string and we use the field code, so you have for instance a program that say a.code, then it will if it's doesn't have a length of 1, if it's one character, it will make an error, and if it's a length of 1, it will look at the Unicode character of it and compile it directly to the code of A, which I think it's maybe 55 or something like this. So here's the kind of thing that the compiler does. If it's an identifier, another one, it will try to type it. If it's a block is a curly brace with a lot of expressions inside it. And if it's a block, then it will try to type X expression, and it will here save and restore the local variables, because the local variables that are declared in the block in Haxe are not accessible outside. If you access X outside of the block here, it will give you an error. So that's basically what the typer does. And then we do optimization. We will skip, and we do the maybe generators is interesting. Let's look at the JavaScript generator, which is the most maybe easy to learn from. It have a list of keywords, and then you have. Oh, this is about the mapping of the source code. I will start from bottom. Usually, when you want to follow a command code, you have to start from bottom, because the bottom is the entry point. So here we enter generate, and then we call functions which have been declared before. So usually, when you want to read a command code, like the order of the execution is bottom to top. So here is a generator, so it says generate, and we'll look at all the types that are being declared. Where are the types? Let me check here. com.types, which is all the types that we generate that have been compiled. We will call generate type for each of them. And then generate type, we look if it's a class, then I have to I will generate it. If it's not extend, for instance, I will generate the class. So you can follow generate class here. And for each of the statics, for instance, I will generate a static field for it. And a static field, it will look at the expression, and if it doesn't have any value, it will print the path of the class and the field equal null. So it will generate a null value for the class, which we can iterate later. And etc. So it does a lot of printing. It's a mix of OCaml and JavaScript output. So you can see like the expression here. We compile the if here. So we print if, then we generate the value for the condition. Then we print a space. Then we generate the expression of the block of the if. And if we have an else, if you don't have any else, then we are done. But if we have an else, then we will look at the thing, add the else, and generate the expression for it. So that's basically what we compile a if in a JavaScript. If it's an array, then we print this character, then we just print all these values separate by comma, and then we print again this. So I hope you get a good understanding of how the X compiler is working. I know it's not easy. I know it's it can be if you look at this syntax, maybe you cannot make sense of it at first. But if you look in details, it's not that much complex. It requires a bit of learning curve, but we have seen in the past that several people like Simon, Dan, and a few others contributors are now contributing on a regular basis to the compiler, and you need to dive into it to start making sense of it, and then hopefully contributing back to it. So thank you. I will look at if there's a few questions you can ask on the chat, which is a good thing about being live, is that you can get questions. Let me check. Okay, what editor you use for OCaml development? Right now I'm using Xdevelop with I have at home a highlight configuration to highlight the keyword and the commands, and it works for me. There's not so much like professional editor for writing OCaml, so I think it doesn't have any like support for completion, a lot of things. So I haven't seen anything that's made me switch from this. So yeah, not much tools in this. Typer.ml is quite a big thing. Yes, indeed it is. I think one of the biggest file, if you look at the source, Typer.ml is 185K, and it's right, it's one of the biggest one, apart maybe from GenCommon, which is, yeah, like this one is from Koei for C# and Java things, and it's one of the biggest file and the most complex one actually. We are thinking maybe like simplifying things here, but it's not yet done. And yeah, basically, yeah, Typer is maybe the biggest because it does the most of things. Typeload is also quite big. It takes care of initializing the class and modules and loading the, if you have a pass, how do we resolve that into a module. But apart from that, it's a lot of definitions. Yeah. This is a macro interpreter, interp.ml, which is also big because you have the whole virtual machine, which is used to run the macros, which run here. And Okay, another question maybe. What is actual target? I will talk about this maybe another talk. It's not the topic today. It's something new I'm working on. How hard will be to add another language like WebAssembly? Well, adding new targets is definitely possible for Haxe. It's been designed for that. So, but it takes some time to actually. You have to write the generator, and you have to pass all the unit tests to ensure compatibility with the specification of the language. And also a big part of the work is to make all the standard library implementation and also with good specification. So you have a lot of unit tests, of course, to check that and to help you doing that. But that's a lot of things to do. You have to understand well the things you're trying to pass. Well, you can get help from us if you need that. We can explain you if you have some error, you're not understanding why you get this error in your target. We can help you telling you why this specification is this way. And WebAssembly is interesting. I have yet to understand how generating directly to it will give some additional performances compared to compiling to C++ using current Haxe, then compiling the C++ to WebAssembly. And I am not sure that there is an actual gain in comparing directly to WebAssembly compared to the amount of work it will require to maintain another target. So I guess right now you can already do WebAssembly with Haxe by doing Haxe to C++, then C++ to WebAssembly. I will recommend doing that, and eventually we can maybe add a few optimizations if you find some problems with the way C++ is doing things with WebAssembly. We can first start doing a few optimizations for the WebAssembly target, but I think in the end it should be pretty much the same as is we do directly WebAssembly. So if the reason is that WebAssembly is not having a garbage collector interface, so you cannot use the native JavaScript collector, garbage collector. So you have to use the HXCVP on garbage collector, which I think will be maybe the main problem using WebAssembly, I guess. No other question? Okay. Thank you very much, and see you next week. Bye-bye.